In example 6, we have a transfer function, which is made up of a linear function of s in the numerator and a linear function, a quadratic function in s in the denominator. What we want to do is come up with our straight line approximations for the magnitude and phase plots that go with our Bode diagrams. Okay, so our first step here is to make sure that the factors here are in a standard form. For example, we have this linear function of s here. What I would do here is factor out a 35. The goal here is to make the constant term in here a 1. Okay, so that's from where this comes. This one, if I write this as s times s plus 5, and then factor out the 5, I get a 5s 0.2 s plus 1. Again, the goal here is to make that number there 1. So we got a 7 from taking the 35 on the top and dividing by 5 on the bottom. So that puts us with all of our factors in standard form. In the end, we have 3 of them. We have a linear function n1 denominator function there of d1 and also d2. In addition to that, we also have this multiplier there of 7. So what I'm going to do is make notes here that are going to help us make our plots. For example, our factor there, constant factor of 7, written in dB, is of course 20 times the log base 10 of 7, and that works out to be 16.9 dB. That's a constant for all omega. N1, if we write N1 in dB, the important things to look at here is that it has a break frequency of 1. Why is that? If we look back here at N1, there's a 1 that's multiplying the omega squared. And since it's a linear factor in the numerator, for high frequency it goes as plus 20 dB per decade along the frequency axis, a decade being a power of 10. Denominator factor d1, in fact what I'm going to do is say 1 over d1 written in dB. It's a linear factor. It has a break frequency of 1 over the coefficient appearing in front of the omega, so that's 1 over 0.2, so it has a break frequency of 5. Since it's a linear factor in the denominator, it goes for high frequency as minus 20 dB per decade along the frequency axis. And then our last factor in the numerator, in the denominator, d2, that doesn't have a break frequency. In log it's going to be exact, but the thing that helps us in placing that on the page is that since it's a factor of s, we know that it's going to be a 0 when omega is equal to 1. Since it's in the denominator, it's a minus 20 dB per decade. The 20 comes from the fact it's a linear function of s. The negative sign again comes from it being on the bottom. So we're going to use these 4 points of observation to first make our amplitude plot in dB. So if you would go to the next page, and what I've done here is I've filled in the numbers on the axes. I put our scale. So please write these down. It's going from a plus 60 to a minus 60. I chose these simply because it fits well on the page. Along the frequency axis, I went from 0.01 on the left hand side up to 1,000 on the right. I've also shown my 2 break frequencies here of 1 and 5. Those end up being important. Okay, first thing we want to do is plot the constant. I've already drawn that, shown here in blue. So this is our dB plot here for our 7 dB, or 7 converted to dB. That was at 16.9. The next one I'm going to show here is N1. I'm going to show that in purple to hopefully make it stand out a little bit from the rest. We realize, or we call that that has a break frequency of 1. To the left of that, for low frequency, it's going to be a 0. So this is how N1 looks for low frequency. To the right of there, it goes up at 20 dB per decade. So I'm going to go up in a way that's crossing over 20 dB right here at 10. And if I continue up like this, that gives us our positive 20 dB per decade. So just to make that clear, that is our factor of N1 shown in this plot in dB. Break frequency of 1, high frequency, it goes up 20 dB per decade. The 1 over D1, I'm going to do that one in green. Again, the goal here is to make it look different than the rest. So it has a break frequency of 5. I've got 5 shown on here. To the left of 5, it's a 0 because we put it in its standard form. But this one here goes down at 20 dB per decade. So what I need to do is have this go down such that at 50, which is, this is 20, 30, 40, 50, we're at that. So I'll try to maintain that slope all the way down. Looks like I lost my end here, so let me extend that on down like that. Okay, so that's the factor here of 1 over D1 shown in dB. Recall in the end we're going to add all these together. Okay, so the 1 over D2, I'm going to show that in orange. Now that is an integrator. We know it has no break for frequencies. It goes across the page at minus 20 dB per decade, and we place it on the page by recalling that it goes through 1 at 0. So I'm going to start up here at 40. Let me try that again. It looks like I missed it. So let me try the 40. That it has to go through 1. So I think if you look back here, that's 20 dB per decade down. So as I go on down the page, I end up here in the lower right hand corner. The key is that it's a 0 at frequency equal to 1. And something seems wrong here because I have got lines that are supposed to be parallel that aren't. So I need to fix up my green line here. It was hard to visualize that, so let me fix that by again knowing that it's got to go through 50. This is 20, 30, 40, 50 at minus 20 dB. So if I can extend that down like that, that looks a little bit better, maybe something like that. Okay, so that's that. So our integrator here, that's going as 1, that is our 1 over D2 in dB. Okay, so we got blue, which is a constant. We have the purple, which is the first order in the numerator. We have the green, which is first order in the denominator, and the orange there, no break frequency. It's the integrator going down at 20 dB per decade. Our goal here is to add these together. What I'm going to do is show that in red. I'm going to show it in darker red, so that's going to be easier to see. So our two frequencies that are important are 1 and 5, because we know we have we have break frequencies in our components, therefore we'll have break frequencies in our composite amplitude plot. So what it means here is that if we start over here on the left hand side, somewhere around 57, it's going to be a bit imprecise here, 57, and it's going to go down the break frequency such that when you're at the break frequency of 1, the only thing you've got making a contribution is our constant term there, 16.9. So that's where that one is. Then between 1 and 5, we see that the integrator, the orange, gets canceled out by the purple, the first order high frequency. So it's going to be a constant of 16.9 across like that. Then once you hit that, then you pick up an additional negative 20 dB per decade. Purple and orange still canceling everyone out here. But the green then dictates the slope from there on down. So it's a minus 20 dB per decade as that. So again, when you look back at this, the thing to visualize here is that the red, which is overall our transfer function in dB, is that's the sum of the blue, the constant, the orange, the integrator, the purple, the first order in the numerator, and the green, which is the first order in the denominator. Be sure to go back and check to make sure that you see how the red is the sum of those. So now let's look at the phase. Again, there are key break frequencies here of 1 and 5, just like there was for the amplitude plot. And again, we have 4 components. Okay, so the first one, draw that out in blue. Well, the 7 dB part has no contribution to phase, so I'll just draw that as a 0. Now recall that for, let's say, the first order, N1 in the numerator, the way we do this is we take note of what the break frequency is, which is 1. But what we do is we go 1 decade back to the left. So I'm going to draw another line here, and we go 1 decade up from the 1, so that puts us over here at 10. And what we do here is that we say that we're interested in, and what did we draw that before as purple? So we know that to the left of 1 decade down from the break frequency, the phase is a 0. We know that to the right of the decade plus 1, it's going to be at 90 degrees, positive 90 degrees, because it's in the numerator. So draw in that, and in the end then we have this 45 degree per decade line like that. So the purple there represents the phase contribution to N1. For D1, recall that that's a first order. And what we do there, just as we did on the other factors, we go 1 decade down from the break frequency. So if that break frequency is at 5, we start over here at 0.5. This is 2, 3, 4, 0.5, like that. We go up 1 decade above 5. So it's going to be a 50, 20, 30, 40, 50, like this. Since that factor is in the denominator, and we're drawing this as green, I'm going to draw a green line to the left of 0.5 at a 0, because that's the phase angle for low frequency. And then to the right of 50, then I go down here to minus 90 degrees, like that. In the end, then I connect these together like that, And green then represents our phase angle for, what did I call that one? D1. Then we need to have our integrator. Integrator, differentiator are 90 degrees. An integrator being in the denominator is a minus. So that one there was orange, right? So if I go with orange across at 90 degrees, minus 90 degrees as that. Got a lot of lines here on the page. We got to keep them straight. We can forget the blue. In fact, just for the sake of not confusing things, since the blue is 0, it doesn't affect anything, I'm just going to get rid of it. You should keep it on your page, but I'm just going to get rid of that. A little bit easier to see. So if I draw this in red, heavy red line like this, we know that it starts out at minus 90 degrees. The only thing giving phase in that case is our integrator. Between the 0.1 and the 0.5, we see that we have contribution here of 45 degrees per decade. I'll try to make that parallel to the purple one there, something like that. Then between the 0.5 and the 1, the green and purple knock each other out in terms of slope. So it's that. Then between 1 and 5, well, I guess that wasn't necessary. What was it? Our next break here occurs at 10, so let me pick up on this and extend that all over to 10, because that's where the next break occurs in purple. And now from between 10 and 50, we have that the purple and the orange knock each other out. One's a plus 90, the other's a minus 90. So it traces down on the green like this. And then at that point, the green and the purple knock each other out, and we got a minus 90 here as that. So let me just add my names that I had here. The purple here was the phase angle due to N1. The blue I erased, that was the constant of 0. The green is the 1 over D1 contribution. And the orange was a 1 over D2. Add them up and you get the red.